To start, I would like first to thank Przemek and Konrad and all of you here. When I look at the website and I saw that today is the 42nd meeting of PyWaw, and I just looked back and we had a meeting every month since 2011. So I think this is something very hard to achieve. These guys deserve, like, yeah. Congratulations. So as Przemek said, I work at Base. It's funny that I didn't come from Brazil. I came actually from China, but you can see that I'm not Chinese. Yeah, I'm from Rio, from Brazil. And yeah, basically, Base is an intelligent sales productivity platform. This means that we have a part of the system which is a CRM, and we build some nice things on top of it, like voice integration, reports, and analytics. And why am I even talking about Base? So this is how Base looks like. Our app is available on the web and on mobile devices. Basically, we are trying to solve a very complicated problem, which is the business software world. And technically, we have a distributed system, which is also something that is not easy to grasp. But for the end user, the whole point is to make something that is very easy to use and accessible. So it's all about making something that is complex to be easy. And somehow that's what I'm going to try to show you tonight. So it was very hard to prepare this talk because I don't really know what you guys were expecting. There are so many things to talk about inside this topic that we could have like a marathon of talks about every detail. So I'll focus about one of the ideas, and I hope like we can talk more about other things you're interested later. So yeah, so concurrency in Python 4. Who here knows, or better, who here have ever used Python 4? Raise your hands. Oh, no one, right? Who one here knows what is Python 4? I am accepting guesses, so yeah, raise your voice, raise your hand, speak. Future plan. The 4K there is, I don't know if you remember, but before 3.0 was released, it was called Python 3K, right? So yeah, there's no such thing as Python 4. I'll just, yeah, forget about that. So when I talk about Python 4, I actually mean what you're going to do after Python, right? Very likely there won't be a Python 4, I guess. Python 3 was enough pain to transition. Yeah, we are still trying to do it. So yeah, my advice to you is to not to drop Python, but to go learn something on other languages and see what you can bring back. OK, so in my case, Python 4 means Go. So I'm going to talk to you a little bit about Go. But yeah, I know I'm a long-time Pythonista. I know you're here because of Python. So yeah, don't give up on me yet, because all the things I'm going to talk about, you can sort of apply to Python. Yeah, and concurrency is this complex thing that, as I mentioned, we are trying to tackle this in an easy way. And let's see if we can maybe take some knowledge that we can put in our tool belt, and next time we'll be able to use more tools. So first I would like to explain what is concurrency, because yeah, it's very easy to be misled by some doubtful definition, or yeah, people kind of think they grasp it, but the concept kind of mixes with parallelism. So concurrency is about composing independent processes. And when I say process, I mean an arbitrary thing. It's not like a computer process, but like imagine like some computation, something that you do. So concurrency is all about composing things, while parallelism is about executing them simultaneously. So they're very related topics, but not the same thing. It's important the takeaway here is that concurrency is about structure. So what we are going to talk what I'm talking here today is how you can structure your code in a different way. I think, yeah, images tell more than words, and to make sure that everyone understands. So it's very common in Brazil that when we go, like every Sunday or in the morning, we wake up and we go drink sugarcane juice and eat pastel. Is that thing there? So that girl is a good example of concurrency. She's drinking and eating concurrently. So she drinks a little, eats a little, drinks a little. You never like drink everything and then you eat, because it doesn't make sense. You also don't eat and then drink. So you kind of have to do the two things in a coordinated way. You cannot like do it even in parallel, right? You cannot eat and drink at the same time. Yeah. And on the other hand, we have here the example of parallelism, where we have two people eating in parallel. And it's important to notice that in order to have parallelism, you actually need two mouths, right? You couldn't have parallelism with one mouth. It's not going to work. Believe me. I tried. Yeah, so it's the same with computers, right? If you want to have parallelism, you do need to have multiple CPUs, multiple cores. Otherwise, it's not going to work. It's not parallelism. Whereas for concurrency, it's just, you can think of it as a design pattern, right? It's just like we have object-oriented programming. You can think of concurrency as a way to structure your code. And you can run these on a single core machine where things don't actually execute at the same time. So Python. Python has support for concurrency, yeah, since long time. And basically what you can find in Python, in this case here, Python 2, you can find basically three things that are related to concurrency. The first one is threading, the threading library. Who here has used it before? Yeah. So it's pretty ancient and common model. People learn it in university. Yeah, it's one way of doing concurrency, but it's also known to be kind of troublesome. Who here has had trouble with threads, where things suddenly does not work, you have no idea what's going on, very hard to debug, right? Problems that happen only in production. Cool, so that's threads. I don't want to talk about threads. That's not the model we're looking for. They differ. I'm not going to go into the details how they differ, but somehow like the API they provide is very similar. So you end up running into similar problems when you're designing your code. The other thing we have, and it started in Python 2.5, like there was a dramatical change in Python 2.5, thanks to this PEP 342. Oh, which kind of is a coincidence, right? We are on PyWaw 42, PEP 342. I don't know who here knows about what this PEP did, like what changes in Python 2.5. Yeah, so one guy, right? This is something that is like hidden in the dark. I think kind of nobody knows about it. Who here has used the yield statement? Like in your own code, yeah. So basically into Python 2.4, the yield had a limited functionality, and in Python 2.5, it was changed in a way that you could send values through yield and also capture exceptions. So you can use this to write coroutines in Python. Coroutines is an interesting concept, which is kind of maps to what I was talking about concurrency. It kind of lets you model things that execute concurrently. And then comes Python 3, and it adds some new tools, and I think that's why like people started to talk about it again. Threading and so on. It's just like no one was interested in that anymore. It was not some sort of innovation or something you do different. So in Python 3, we have everything we had on Python 2, plus we have concurrent futures and async.io. I think everyone here, like async.io, maybe all of you have heard of it. Am I right? Yeah? Yeah. Okay, good. So I had like mixed feelings about async.io. I mentioned in the description of this talk that I would kind of complain about the current things in Python. Somehow, like, I don't want to be like very mad on Python 3. I think we are, at least in some way. Okay, I think we're back. So yeah, we have kind of a concurrent event here, right? Like two things happening at the same time. So yeah, so async.io, I said I have like mixed feelings about it. Just like I see that no one grasped yield and no one is using it in their own code, or at least like very few Pythonistas are doing it. Using async.io requires you to change the way you use Python and introduces yet one more thing called yield from that I also don't believe people are actually going to understand that and use that. But I hope I'm wrong. So like I look at the Python website and it has this note in the async.io library, and it's kind of scary. Saying like it's there, so it started in Python 3.4. It's not in Python 3, 3.1, 3.2, 3.3. It's only in Python 3.4. And it says like, oh, it's here, but yeah, like don't trust very much. I don't know, maybe we remove it in Python 3.5. And I hope no. But yeah, let's see. So back to concurrency and beautiful world. I said like we're not gonna dive into threads or the threading model, basically because we are looking for something else. We are looking for something that is easy to understand, is easy to use, is easy to reason about, will help you avoid making mistakes like deadlocks. So you don't need to be an expert on threading and managing the separate things happening. No, we want something that people will actually use it. People will learn about it, they will like it, they will have fun with it, they will write correct code. So let's see what we can do about it. So the first thing is, yeah, maybe you cannot see very well the top there. I have like two axes. One is time and the other is the work you get done. And in a normal sequential program, basically what we do is like we have this main function, which in Python is like whatever the interpreter is doing, right? You can think like if underscore main, like, underscore name equals main, then do something. So you have like the main flow of your program, your main thread, your main process. And basically what you do, you're calling functions, and these functions might call functions. And it's all sequential, right? That's what we do. We understand this very well. Yeah, so there is a model that let us introduce concurrency, and our code will be written in a very similar way. And this model is called CSP. It stands for Communicating Sequential Processes. It was something first introduced in 1978. So yeah, like I was not even born and guys were already studying it. And it's something still in active development, like people are still researching this model. And there are some nice algebraic properties, like you can prove that things work. And with these tools, which is like computer science, right? Like we're computer scientists, engineers. So with these tools, we can, for example, prove that a program is right or not. And that's pretty useful. For example, in the Go language, which is something we're going to see, we have something that is a race detector. So before, when you have threads and you run it, you hope that your code always works, but you never know. And when you have like a race detector that can analyze all of your paths of your code and tell you whether there will be a race condition or not, then it's awesome. Like you just run it and it tells, oh, your program is correct. So you just put it in production and you are happy. So how does the CSP model works? It's still very similar to the sequential mode. So you basically have now the two processes running. You can think of process A is the girl drinking sugarcane juice, and process B is the pastel, the delicious food. I'm missing it. And I'm gonna get it in a month when I go back to Brazil. So yeah, you can imagine these two things. And you can think that each of those purple arrows are like either like one bit of drinking or one bit of eating. So you basically, each process still do things sequentially. So for like the process that just eats, you're still eating that snack like sequentially, and it's like disappearing in a very clear steps, like until it disappears totally. And somehow like you need some sort of way to communicate when and decide like when you stop eating and start drinking and so on. And on CSP model, what you have is a channel, which is this way to communicate something. So from one process you can send a message on a channel, and then the other channel will grab this message and do something with it. So basically in Go, this notion boils down to three primitives, three concurrency primitives. First one is a Go routine, second one is channels, and the third one is select. We're gonna see like them one by one. Can you hear me well or not? Okay, good. So yeah, first one, Go routines. So Go routines and making a parenthesis with Python. Who here has used gringlets in Python? Yeah, so Go routines are this thing in Go that represents the CSP process. And it's very similar to a gringlet. And the gringlet is like a thread, but with a lot less resource consumption. So this is like very, very simplistic definition, but you can think of it as a thread, as something that you can execute independently, but it consumes very, very low system resources. So you can just have millions of them and it's fine. The other difference is that threads, they are normally preemptive. That means that there is some scheduler in the operational system that says, okay, this thread stops running and the other one starts right now. So your thread doesn't control anything. Whereas with Go routines, gringlets, and coroutines in general, we have what is called cooperative multitasking. So basically your code is like single-threaded. It's always running unless it says, oh, I want to stop, and then it gives control to someone else, to something else. That's what we do with Python. That's what we do like with coroutines, simple coroutines based on PEP 342. And that's what we do with gringlets. In Go, it's going to be this Go routine. So I have there like 3 lines of code just for a brief explanation. Imagine you have like a very, some function that it might be fast, it might be long. You can imagine that, for example, it does some HTTP request, or it talks to a database, or it waits for user input. These things can be like very quick, milliseconds, or it can be very long. It can take over a minute, it can fail. So in normal code, what you write, like if you're writing your sequential code, you're not aware of what else you can do, you're just gonna call this function. Sometimes you don't even know, you don't even care that it might take long, right? And I think that's how we end up writing our applications. I think there's a lot of people here that write web applications. And inside our views in Django, we don't care. It's just call functions and pretend that it's gonna be fine and it's gonna be quick, but sometimes it's not. And when you have a Go routine, how to make it a Go routine? In Go, it's very simple. You just say Go and the same function call. And the difference here is that you don't block your flow. So if you're calling this from some function, you're still in that function, and you're just saying like, whenever there is time, execute this call here in some other, environment. So like it's running on a separate Go routine, is the separate process. Is that kind of clear? This is like saying the first one here like might take long, is the normal function call, and then swapping for start a new Go routine, you just put the Go in front. It's that simple. So the contrast is that with Python and Python 3.4 async IO is not just that. You kind of have to do if you like, it's not a function and you know that that's a coroutine, so you have to use UD from the call to the coroutine. So Go is this simple. Then we have the second part of the puzzle, which is channels. Channels is it's a channel, right? It's just bidirectional communication thing. You can create channels in Go by saying like make channel and you say the type. So I'm not here like to teach you Go. If you're interested, like I think you can find like golang.org and go for a tutorial. So Go is like typed language, static typing. So when you create a channel, you say what is the type of the channel. But important thing here are the two other parts, is the communication. So you can send messages on the channel and you can receive messages from the channel. And that's basically the only tool we will have to synchronize the work between two or more of our processes, of our Go routines. Then the third piece, maybe we need like to take a breath and to absorb it. The third piece is like the other two, they are nice, right? You can start another process. You can communicate with these other processes if you use a channel. But then sometimes you just you want to do some sort of operations that is similar to something like, oh, okay, there are like these few things here that are happening, but they might be blocked, right? So you have those calls that are like, let's say you're downloading 3 things simultaneously, and you need a construct to say, okay, whenever one of these things is ready, I want to do something. So the construct for this is select. It's also known as alt, A-L-T, like in CSP model. Some other languages implemented with that name. So you can think of select as this kind of switch statement that do things concurrently, right? So it says whenever one of these things in the select statement. So you have there like on the first side, like select statement. Whenever one of the cases is ready to proceed, normally like you have some blocked call there. Whenever something is ready to proceed, the code will execute immediately. So I'll go and explain this piece of code in particular. So this is one implementation of Fibonacci sequence. So unfortunately, I don't have like a pointer, but yeah, like follow with me. First line on the left. So you're declaring a function that takes 2 channels, see and quit. C is basically our output channel. We are going to write the Fibonacci series to this channel. And we use the quit channel to notify this function Fibonacci that it should stop running. So we'll go back to it. Let's see the main. So everything starts in main. So what you do, you want to use Fibonacci function. So you create 2 channels, see and quit. And then you start, and here you have like the Go func. You have like a function literal. And you're just basically saying like, start on a new Go routine, a loop that goes from 1 to 10. And it tries to print some value that you just read from the channel. So whenever you go into that line, reading from the channel, there's nothing there, right? I just created the channel. So reading from the channel is going to block. That's where we have the moment of synchronizing the 2 things that happen in parallel. We will have main and Fibonacci running, sorry, not in parallel, concurrently. So we are there in format, print line, read from C. That line is going to block. But it's okay because we are in a different Go routine. It can block. Whenever the for finishes, we send some value in quit. And this value is just to tell Fibonacci to quit because we don't want to do anything more. And then in the main Go routine, we call Fibonacci passing the 2 channels. So we need to pass the channels because otherwise there's no communication between these 2 Go routines. And then on Fibonacci, what we do, then comes the select statement. Because either one of these two things can happen. Either you can read from quit, which means go out. So that's the second case there. So whenever there is some value available in the channel quit, we'll just print something and then return. And the other case is whenever I can write an output. And whenever I try to write an output, if there's no one reading the output, this is also gonna block. So that's when these two things, and they're like in very, almost in the same line here if you look. So writing in the channel C and reading from it, that's the point where you make the two processes talk to each other. So there is one process saying, oh, here's the next number in the series. And then you like throw it in the air and boom, freeze the world. And then there's someone, okay, I want to print the next number. So he catches it and prints, and then the whole thing continues until you print the 10 first numbers and then you quit. So that was select. So now I'm going to show you like a potentially real example. It's not a real example. I would like to do it, but somehow like I want to also keep it like short and we can discuss things as you ask me. So the example here that I think is like very nice to think about is how does Google search works, right? So Google search is like a very tough problem. So we're not going to solve it with a few slides, right? But we can think of it as how to structure the Google search thing as the composition of independently executing processes, right? Our definition for concurrency. So yeah, just make sure you're all on the same page. Google search, you go there, google.com, you type something, you click search, or you don't even click, right? It knows that you just typed and it searches. And then it's going to show you a lot of results. Like it's going to show you the normal web results. It's going to show you like what videos have something to do with this query, what images are related to this, and so on. So one way to translate this thing into a series of concurrently executing processes, we can do it like that. So we basically say that Google is a function. It takes a query and it returns a bunch of results, right? And how do we combine these things together? First thing we need, we want a channel to communicate, to pass the results. And then we're gonna have like 3 Go routines that we start. And we just call a specialized process to do a web search, and then a specialized function to do image search, and a specialized function to do video search. So you're basically starting concurrently. We are starting concurrently 3 searches, which is very different than like search on the web. Imagine if you go to Google and it's like that. Like you type the query and then it's like, oh, here are the web searches you have. And then 3 minutes later it says, oh, but there are also some images if you keep scrolling forever, and there are some images, and right? This is not how it works, right? All the things happen at the same time. So that's how we map it into the CSP model. We just say start these 3 things concurrently, and then we communicate by sending the result of each one of these processes to the C channel, right? It's the channel that takes results. And then what we do in the main thread is just easy. We just keep reading from this channel of results, and as soon as some result is ready, we append it to this to the result list, which is basically what you're gonna return. So this is basically like start web, image, video concurrently. Whenever, in whatever order, whenever something is ready, append it to results, and then Google returns a result for you. And you can think that later what you're gonna do is just like some CSS, JavaScript, and put the things in the right places in the page. But you have it all. So one more thing we can do, which is a nice thing you can use in your code. And see that example we are talking about Google, but you can certainly use that in whatever program you're writing right now. I believe there are clearly things that you can see this pattern, that there are things that needs to happen, and they kind of could happen concurrently with some communication to like aggregate results. So I believe you can all apply this to your code. So the other thing we can do is like imagine if the image search is slow. So if it's slow, it's gonna make slow the whole search, right? So if you have to wait for 1 minute for a result for images, it would take also 1 minute to get the whole thing. And yeah, Google wants it to make it very snappy, that you keep using Google, right? Because you just click it and it's, oh, everything's already there. It's so fast, it's so nice. So what we do, we put a timeout there. So we say we are gonna search these 3 things, but if any of them, or if it takes more than some time, I'll just stop and show the results I have so far. So that's the code for that. The same thing, like I started 3 things concurrently, but then I had this timeout thing. And this time after 80 milliseconds, what it does is this is a function call that returns a channel. So with this channel, what is going to happen is that you want to read from this channel, and after 80 milliseconds, this function that you just called is going to write on this channel the current time. You don't really care like the current time, you just care that there will be something written on this channel some milliseconds later. So what you do, you use select. So then you have again the loop, like waiting for the 3 results. And now there are 2 things that can happen concurrently. You either have a result from the C channel, as you had before, but now you can also have a timeout. So the select fits perfectly here. Like there are 2 things that can happen. I want to react to whichever is ready for me to proceed. So if there's a timeout, we just return, which is actually going to return whatever results I have so far. Otherwise, I'll just keep appending results. Yeah, we could go like much far from that. We could, for example, add like redundancy, so we could do the same search on replicas for each thing, but we are not going there. I'm gonna go back to Python. So as I promised, like I want to tell you how you could try to map this into Python. So basically, if you're still running Python 2.7, probably the best way is to stick to gevents, And from gevent, you can use greenlets and gevent queues to just make the same kind of patterns. So you'll be able to choose greenlets as the go routines, and the queues will play the role of a channel, so that you can map whatever you need to code as a series of things that are independent and they communicate. Yeah, I've done that in the past. It's very cool. So for example, if you want to do like parallel downloads, yeah, just do that. Just use that. And then if you are like adventurous and you want to join the new thing, if you are on Python 3.4, there is async.io. In async.io, you have the coroutines package, and you also have queues. So there are different queues. Like, don't confuse. There are different things, but they allow you to, again, like where we are focused on the structure. There are a lot of things that, like we could think of. There are like different approaches. People will talk about gevent and like having to patch the whole world, but we're focused on the structure for writing your code. There is one more thing, that the third one is this called Python CSP. There is a paper about it. I haven't really used it. I think it's not like production ready, but if you just want to like understand the concepts, it's also something very good. You can search for it. It's on GitHub. So there's like source code and a academic paper about it. So it's basically the implementation of CSP on Python. So there are other languages that also implement CSP. So the first one was this language called OCaml. There's another one called Limbo, and these two are not very popular languages. So probably the other language that you heard of is Clojure. And there's a very nice talk from Rich Ricky, the creator of Clojure, sort of defending this model of CSP as being really easy to use. And he implemented this in his language, Clojure. So if you're using Clojure, you can also use this model. And Go. So Go is the kind of the language that popularized this. It made it very easy to write concurrent code. As you saw, like, you just have these three primitives, and concurrency is really part of the language. So whatever you do, it doesn't feel like you're doing something crazy, like that you need some external library that is not supported. No, you're really doing what was meant to be done. So we'll finish here. I have some links, and I want to hear your questions now. Yeah.
Do you hear about a fork of Python named Stackless Python?
Yeah, so the question was, did I hear about Stackless Python? Yes. What about Stackless Python?
Okay, there was implemented coroutines and the channels.
Yeah.
So you're proposing that it should be involved this way.
Yeah, so the idea, like one of the original ideas behind Stackless Python is that it wouldn't be like a fork, but it would be actually integrated to Python. But it never happened. Probably it's never going to happen, as Guido says. But yeah, it had some nice things. Just like PyPy also have some nice things that you don't have with CPython.
Okay.
So
If you mentioned about PyPy, there is Greenlet with the current. Do you think that it's a good idea to implement that library with this continual lets?
yeah, so as I said, like there are a lot of ways to go into this topic. For example, people might ask about like async IO, right? Just using and async IO, I mean like asynchronous IO, non-blocking IO. So like just using PyPy something, you can use a lot of tools. And the point here is it's not about the tool you use, but about the structure you give to your code. In a way that is going to be like easy to maintain, easy to prove right, easy to write, easy to understand. So yeah, like using PyPy, you can use like the things that are specific to PyPy to write like a very, very similar structured code.